start those kind of discussions, I normally do this one. Do you do that? You never do that with water, right? It's precious. But this can also be 2 million euro, and I have poured that away on the floor or in the drain because the quality was not okay. The product quality was not okay. And my colleagues, what did they ask me? Not why did it happen and what did go wrong. They only asked me, when do we do it again? And let's hope next time it will be better. That was the time when I was in biopharmaceutical business, and then I decided we have to do something else. We have probably to think about proper methods to solve these issues and be predictive and allow these product quality to be predictively well, all right? That was my move. Sometimes you have to suffer on certain elements in order to probably change something, okay? So that's this story with this bottle. So it's about life cycle, it's about control strategy. So it's about the result of the CMC work, right? And the task in biopharmaceuticals is here. I think these are our business goals. We want to be very quick in commercialization. So you see the life cycle from development to manufacturing. We want to have a robust tech transfer and successful one. And then, of course, we want to have zero batch failures in production. I also grayed out the supply chain thing. That's not my work. I'm not really focusing on that. But the other elements. And then you have on top, you have the life cycle management. Also exemplified via ICH Q12, right? And I think that's very important to mention that whatever we do, we not do only once, okay? So all business processes and data science methods, whatever we do, have to be made for continuous improvement along ICH Q12. I think you're aware of that very much, right? So what is the task, actually, to fulfill this kind of thing? It's just this simple equation. So we just have to get the quality right on the right side. And we just have to find the relationship to the CPPs, to the raw material or critical material attributes, and that's all. Then we are done, okay? The question is, it's not that easy. CQAs, we have about 15, probably in any biopharmaceutical business, whatever. And we have probably along the process chain about 400 CPPs and probably 100 CMAs or 15, probably we don't know them even. So the uncertainty plays a role. So this is the equation which we have to solve. It's a multivariate, multidimensional problem which we have to address here. And there are two steps which we have to do to get a control strategy. First, we have to get the understanding how these things are related. And then the second thing is how to actually maneuver in there, right? I think these two steps we have to do. The control strategy, for those of you which are not probably familiar with that, is mainly exemplified in ICH Q10. And it's about the linkage of the complete process chain, I will come back to that later, to, let's say, the drug substance, drug product, or probably the patient. It depends a little bit where you put actually the envelope, right? And when you work in cell and gene therapy, probably you should really go into even looking at the patient more. So we have to set up control strategies, and I quote here something which we have also published here, the article of the year, something in ISPE, on holistic control strategy. What's the difference between a control strategy and a holistic control strategy? If you set up a normal control strategy on the left-hand side, this is what you submit, and then, in the future, the manufacturing, so that's the right side of the picture, will give you additional challenges. So there will be variability from the equipment, from the biology, from the aging of the equipment, of manual interactions, etc. Lots of different elements, which all come from the life cycle and the scaling. And the control strategy has to anticipate those kind of elements, right? They have to anticipate all these changes, how to do that properly. And this is the holistic part of it. The control strategy can be implemented in probably 3 different levels. This is a slide from Lawrence, a friend quoting this, that the level 3 is, of course, where we should not be in. It's end product testing, right? It's about this bottle, right? Okay, I always count on that. But we should move off that, right? We should see the performance-based level. This is level 2. At least we have some process understanding, and then we are maneuvering inside of the design space. That's fine, right? But explicitly, when you think about intensified bioprocessing for continuous biomanufacturing, etc., you don't have time, right, to really take a sample, etc. So then we need to move to the upper part, which is the real-time automated control, flexible process parameters to respond to variability in the input material attributes. Big thing. Are we there? I want to show you with my presentation a little bit how we can actually achieve that and get to level 2 and level 3, okay, here. Yash motivated this conference by saying, yeah, we need a kind of how approach, okay? How do we really do that? So, and I want to show you a couple of elements here in this direction and some prerequisites. If you want to get something robust, you have to tackle variability, right? And the variability you have to identify, you have to monitor, you have to control. There are a couple of methods which are around of that. Of course, there can be models to identify this. This is monitoring, which is PAT, so process analytical technology, which is a big part, which actually always runs into that. And of course, data science. We have published these kind of things also here in the PE magazine here on data science for Pharma 4.0. This is something with MIT and a couple of companies, Merck in there. So probably have a look. And also in this orthogonal therapy good practice guide just recently, where wherever you are actually moving in what kind of product, the task is always the same. It's tackling variability. Right? Look at that, okay? And variability, of course, probably you can measure. It's nice. Probably there's also uncertainty in there and how to tackle this one. You saw my comment yesterday in this conference. How to do that? So one enabler of that is definitely digitalization, okay? In order to do so, and then a digital twin. So let me go step by step. So you see here a picture of German. Oh, shit, it's German. So this is the German initiative on how to bring digitalization in process industry. And we were sitting together and thinking about a couple of hypotheses which we need to follow in order to integrate digitalization in the process industry. Not only bio, but in process industry. And the first thing is written here is about das Überleben in German, so it's about surviving. So we had that yesterday. If you are not adopting digitalization, it's not about that you are just back in business, back in its development. You're not surviving. That's the basis, okay? That's the prerequisite. You have to move in there. And then the question, how? And there are a couple of hypotheses along that line, which I probably want to show you. Here is one. The digital twin is the basis for, let's say, integrating digitalization in the process industry. And I like the last sentence here. The loss of a digital twin is a loss of know-how. Yeah? So I would like to emphasize that I believe that the digital twin is a means to capture knowledge and to deploy knowledge, actually. And we will see some examples here in this keynote. Okay? It's a loss of know-how, and the digital twin can be, of course, in many different dimensions. You see here the different dimensions of the supply chain dimension as well as the asset life cycle, these two elements, right? And there can be a digital twin for all of that, okay? I'm not building a digital twin for all of that. I mainly do work on the asset life cycle in the development and transferring that to production. And of course, there should be also twins in the supply chain area. It's not my work. And finally, of course, when you think about Pharma 4.0, it should be somewhat connected, right? There's no doubt. So that's the motivation which I wanted to give you here. So digital twins. How to set them up and how to deploy them. So what are the benefits, right? I will keep, let's say, the development very short. This is more the scientific part. I don't want to frustrate you here on that, but there's a message, and then mainly focusing on the benefits on that. everybody says, yeah, digital twins are mainly done by AI or machine learning, and all this is great. Think about that the problem which we have in the control strategy is that we have so many parameters, process parameters, etc., which may influence your product quality, and we have so less observations, right? So lots of P's, parameters, and less of N's, yeah, so observations, that we have a completely different approach than what Amazon or Google is doing. They have big data. We don't have big data. We have a problem to identify these parameters, right? And we have, well, how can you solve an equation of, or an equation set with 400 unknown parameters, let's put it like this, okay, with 50 observations? Very difficult, right? Therefore, what we need to do is we have to constrain the problem, okay? And the constraining the problem cannot be done by machine learning or AI. It first needs to be constrained by domain knowledge. Therefore, I always say, please start simple, okay? If you set up these systems, start in the lowest complexity with the highest maximum, highest mechanistic information, and balances do not lie, okay? I think that's the first approach. Use the balances, and then, I'm realistic enough, you have to move to the right in this picture, okay? They have to move to opening up the black box. You have to see actually what is going on there. And then, of course, you cannot explain everything in a mechanistic way. Then you have to probably put some data-driven elements. When you think about just the influence of pH, let's say, on cellular metabolism, it's very difficult to explain that mechanistically. I think you are with me, right? So in this way, there will be, of course, data-driven parts, and the real, the truth will lie finally in hybrid models, okay? So on the right side, it will be a combination of these things, and we are building hybrid models. I will show you how we do that. But before we go into that, how to set up these kind of models, I even animated that slide just to show you that what we are doing here can be done in an automated way. We are using, for setting up these digital twins, we are using GMP, good modeling practice. This one doesn't need to be reinvented. There are steps which actually get to a minimum targeted model. Here, for example, just estimating viable cell count, let's say, something like this. And of course, you can model an elephant with 60 parameters, right? But there is a huge risk on overfitting, and there is a huge risk that you have many parameters which are actually collinear, and you cannot really differentiate, and you have multiple solutions, right? You have to make sure that you actually calibrate your model, that the model parameters are purely identifiable, and you know the sensitivity of these parameters, okay, to keep that short. And this is all done in this workflow, and it can be automated. We have done that, and we do that for many companies. We do that as services, and we implement that directly, okay, this modeling practice workflow. So depends on the data if we can really do that. Probably if this kind of set of equations is not sufficient to really reach your goal, right, then probably you have to enhance the data set and you have to go step by step, right? But first we say, give us what you have, and we look how far we can actually exploit that. Before we say, oh, we need all the data. That's not the point, okay? First, let us see for the certain goal if we can reach it with this data set, okay? And therefore, we spend more time actually in defining the goal than actually we need time for the generation of the digital twin. Yeah, you cannot have a data set and say, let's model this. We'll set a clear goal with clear acceptance criteria, and then you will be successful. We also use, of course, machine learning. What people say here is an artificial neural network, because everyone who is modeling knows that you need very good rates, for example, let's say input rates in order to do that. And we are using here machine learning, artificial neural networks to do that. You see in the right upper corner how we have machine learning on one side, and then we have the mass balance, so the model afterwards. So we are combining, let's say here, probably machine learning to estimate something with a mechanistic model. So you see that the hybrid could be, let's say, a sequence But it could be also the other way around, first the mechanistic and then the data-driven, or let's say they are running like this. So it depends a little bit what we do. I don't want to confuse you, but these things are there, and these things can be used. And like this, we get wonderful models out. So this is what we can do. And then, of course, these models need to have a life cycle. Okay? That means we are not, when we apply now a different data set to this model, we are not only, let's say, changing the model parameter values, we are allowing the system to probably recheck if the model structure is completely the same. So the linkages could be a different one, the reaction scheme could be a different one, etc. And this is all also the adaptive nature of these models we have also automated. That means if we have a certain data set here in green, and then we run this model, then actually you see also the vertical lines changing there. So actually we are changing the phases, we are changing the reaction kinetics, etc. And we get a multitude of different possible models out of this, which we can finally select for proper process control, right? So these things are there, okay? And the good point is we are independent of one modeling nerd, which we are all dependent on probably, and if he leaves, everything breaks away, okay? I think there's always a problem with these models, right? They have a negative perception for that reason. I think we can change that if we have automated that, okay? And the data science methods are all there. So that's about how to set that up and also, let's say, to get these adaptive. What to do with it. Of course, we have to identify CPP, CQA relationships, okay, to get process understanding, and of course we can DOE. But a DOE is only the solution in case you have no idea. You shoot actually blindly in all directions, right? It's an explorative approach, okay? And then you find out what is actually related there. If you have knowledge, if you have, for example, this kind of digital twin available, you can make use of it. So we are going very much on the right side of this and make very targeted model-based design of experiments. They are much more targeted and there are much less efforts experimentally needed on that. Think about, let's say, when you have this normal cube, the statistical design of experiment, you have to set the boundaries. You don't know if these boundaries are okay, if you can actually execute them. You don't know where the optimum actually is, and probably after this cube, you have to run a different cube in a different area. So you have one cube in another, and so which you have to set. If you run model-based and you're actually optimizing information, so Fisher information metrics would be, let's say, the keyword in this direction, you don't have to set the boundaries. The system will find the boundaries by itself and the optimum in there. Very, very neat approaches. So message is, if you have knowledge, use it also for experimental design. You can use it here, for example, we have done that with a company in Germany, optimizing the feed strategy for CHO culture. Here, you have to always add every day certain bolus shots of certain feeds. Okay, every day you add something, so normally the red on the lower bottom part, you see all the red additions. Okay, this was the normal way. And you get out the dash performance on the titer, you see on the right upper part, and a certain critical concentration, and like this you performed. And if you have a model, now you can start thinking, okay, what would be the best addition strategy? Okay, you run an optimization algorithm, a genetic algorithm, or whatever, in order to maximize titer. Okay, then this is in silico work. And you see the blue one is, let's say, a completely different trajectory, which we are having here on the lower bottom corner, okay? We have a completely different, let's say, addition profile, and also a completely different resulting concentration of the limiting amino acid here. And then we finally got just 20% more titer. And of course, we do a verification experiment on that. But if you would do that, let's say, in an experimental design, you have actually 13 bolus additions, right? You would have 13 independent events which you need to design. Good luck for an experimental design in this direction, okay? So if you have a model, use it also for experimental design. But there's only one thing. So more important, when you think about the control strategy on level 1, right, the real-time thing, we have to bring the digital twin in real time. Okay, and I want to show you how we actually do that. So we link the process on the left side to the digital twin on the right side. We have PAT in the process. We evaluate the data. We feed it back over our tool into the digital twin. And then you have actually on the right-hand side, you have two elements. You have one, the state observer algorithm, and then you have the model predictive control algorithm. And I would like to show you probably both elements, what you can do here when you deploy the digital twin in real time for those two cases. Okay. First, the state observer algorithm is mainly the thing which just predicts. It just predicts what you are going to see, process events, etc. I tell my students always, hey, if you do that, you know when you can go home. It's a very good thing for them, right? So you actually have this digital twin. On the right-hand side, you see the data coming in real time, and then you have your model-based prediction, kinetics, where actually we are ending up and when nothing is happening. So you can do that for identification of the harvesting time point, identification when you need to feed something, when you go home, when something goes wrong, all these kind of things. Yeah, these things. And in the middle, you have this kind of observer. It's a particle filter. It's a Bayesian approach where you actually do a state estimation between the process itself and the digital twin. So it aligns actually that. It's also something which is there since 20 years, right? This is, of course, something which applies also very much in intensified bioprocessing. And in continuous biomanufacturing, I just wanted to show you our approach on continuous biomanufacturing is another example. If we run continuous, we need to have some measurements. They may be very scarce in the moment on CQAs, right? The quality attributes can hardly be measured along the process chain, right? But there's probably a solution, and this is if you actually link the digital twin to the system. Because the digital twin is actually linking CQAs with CPPs, okay? It links inputs and outputs. And if you have this twin established, you only need to measure one of these two, okay? It's a means to measure less, you can imagine, right? So if you measure only the CPPs, you can extrapolate what will be the output CQAs. And then you probably get rid of these elements, okay? That is one thing, okay, what you can do. We established these things in our lab here. We are not just in silico guys, okay? We always verify our stuff, okay? Here you see actually our setup, which has reactors and online, let's say, sampler system. And the main idea is to get the reference analytics, which you normally have in your QC, okay, directly to the process in this sense, okay? So you get the PAT tools directly. Of course, I had the process, but these are the reference analytics. With the goal, actually, to get rid of additional QC measurements. So actually, you can directly use these tools for the QC release, okay? Here, I just got something in here. I'm working with Agilent on this here. We also get MS-TOF for CQA measurements online into that. So that is also an interesting thing that you directly measure CQAs then directly on this, okay? But that's on the long run. So the main message is here, it's not only about digital twins, but it's always also the link to PAT, and you have to think both. But first set up the digital twin and think about what the digital twin, so the set of equations, really needs to be observable. So define your PAT strategy. So define what elements you really need to measure based on the formulation of your digital twin, and not the other way around. Not say, oh, I have a Raman system and then I measure. Doesn't help at all, okay? Turn it to have an observability of the entire process and go from there. And then you select the measurement which you really need in PAT. I give you an example on continuous manufacturing here in microbial world. It's probably also interesting. For those of you which work in microbial world, you know, okay, you induce the system by hitting the cell on the neck and say, come on, you produce now a product which you don't want to produce, and I take into account in 4 hours you will be dead. Okay, that's what's happening. This is this steep curve, okay? But if you think about continuous manufacturing, this one will not work, right? We have to have happy cells, and I like that we are all alive, okay? So in this way, we have to move that in a different concept, right? We have to have tunable promoters. We have to think how to get to this more, let's say, stable, specific productivity here. We can already do that if we change the feed here, for example. We have done it in earlier times, patented also with Lonza earlier. But then still the QP is still better. So you see the green line is already getting to the target, but it's not okay. But what we are now doing is we have a digital twin. You can invert the problem. Okay? So we go backwards. Okay? We say we want to have a continuous, constant, specific productivity, and we say, hey, my dear digital twin, how should the feed rate be? Okay? This is what we are actually doing here. This needs some more enhanced control laws. It's a feedback linearized control law, which is quite difficult because it's a highly non-linear problem. You can imagine, right? All this is a highly linear problem. And you finally go to control a linear flow rate, if you like, okay? The control law is a bit difficult. However, what you see here, you get much higher product. You see on the lower right corner with this strange black, bold feeding strategy, which is not obvious, right? So these things we are doing. Also here, the message is, if you have a digital twin in real time, you can invert the control problem, okay? And really run and enable continuous manufacturing, else you would have never thought of doing that, okay? I hope you see the benefits. We have also deployed these kind of digital twins in 100 cubic meter scale here. With model predictive controlling, a controller, so feedback control, right? Model predictive control, MPC, compared here to a classical PID controller. Those of you, yeah, so this is only looking at a set point, and it, of course, UPD just follows the set point. You see it on the left upper corner, right? It just follows this, right? But the MPC is doing something else. When you see the right upper corner, it actually deviates right now from the set point. You see that? Why? Because it's predictive. It means it looks in the future, it has a certain prediction horizon, and from there it actually looks, okay, what will happen? How can I optimize my productivity? And when you see the lower right plot, it has actually increased productivity compared to the PID. It has seen, if I would have run on the set point, there would have been a metabolite formed or any side product formed, which would have been negative to my objective function of productivity. We do these things, and this is implemented in industrial GMP biotech 100 cubic meter scale, okay, with Novartis. Yeah, so this is finally giving us robustness, and it's a very much sound control strategy, okay? So far, we only looked at one single unit operation, okay? And we are optimizing that one. But finally, if you think about the control strategy, it's all about the complete process chain. So what do we do on end-to-end control of the system? In continuous or not, it doesn't really matter, but how to actually get to the final product quality, right? And not only optimizing individual steps. So here, the task also of the control strategy is, of course, getting the final drug substance, drug product, or patient quality, whatever, right? Right, okay? So we have to make sure that this is happening. Think about this bottle. What's the problem? If we now have optimized each of these unit operations, we control each of these unit operations, and we have a certain normal operating range, and the operator is trying to stay at the set point. Right? Inside of the normal operating range. Probably he goes a little bit left, a little bit right, but still in the range, okay? And the next unit operation, you will do the same. Not exactly as I said, but a little bit left, a little bit right, okay? And so on. And so the point is the interactivity between the unit operation. We have done so many root cause analysis of out-of-spec events where all the MBR, the EBR, and MES was all fine. Everything was wonderfully settled. But the root cause was the interactivity between the operation. Okay? So if you switch a little bit less, that the interactivity drives you to fail. Right? Think about this bottle. Yeah? Nobody to blame, it looks like, right? Because everybody has done his job. But this is really what happens. So what we need to do is to think about a holistic end-to-end control strategy which takes into account those kind of interactivities. You can do that with linkage studies, of course, spiking studies and cross-characterization. So you spike here or there. Best would be to spike it even in manufacturing. You will never do that, so you do that in your small scale, of course. You see, very, very difficult to do that, right? So we have to find other solutions. And what we are doing is doing this approach with a kind of integrated process model. I show you how that actually works. So we are feeding here certain input parameters from one to the next step, and we're actually propagating the distributions of the inputs and the outputs over the full process. So we can do that with the Monte Carlo simulations. And then we see finally the out-of-spec probability. Here, for example, you see how you actually identify a certain intermediate acceptance criteria. So the specification of a certain unit operation 3 here. Okay, what is the specification of a certain CQA, and how does this actually directly influence my drug substance quality? And inversely, if you set a certain drug substance quality at the end with a certain probability to fail, for 5% or hopefully less, 1%, right? Then inversely, you can identify an intermediate acceptance criterion like that. Very helpful to do that, okay? How else do you develop a certain process if these intermediate acceptance criteria are probably not known, right? So here you see how that gets out. There's a parallel coordinate plot here for a certain CQA over the different unit operations. And you see that there are a couple of elements combined. So these thin lines are the batches which have been run. The orange lines are the classical 3 standard deviation approaches over that, okay? And 3 standard deviation approach is absolutely insufficient for that kind of work because it gives you no idea on a probability of failure. 3 standard deviation is not computing any probability of failure, right? So here you see that the purple line is actually the output of the integrated process model. And in the earlier phases, the model is constraining the problem a little bit more. And in a later phase, it actually relaxes the specification. Okay, so we are doing this with Boehringer, with Takeda, with lots of companies in this direction to actually set up proper control strategies. The same thing you can do for calculating then your normal operating range or your proven acceptable ranges. So here, for example, you switch your elution pH, right, of this first chromatography column, and then you see what is the probability of failure on the right-hand side. Or inversely, you can set your proven acceptable range according to what you accept as a proven as a probability of failure. Yeah, those things can be done, and they're very helpful. So this one we can tie together. That means we have identified individual models. I showed you that, how to actually do that. And if you have these models available, right, already, we can already integrate them into these process chains, okay? So we use completely different models, mechanistic models I've shown, linear, let's say probably also just regression models. We like linear mixed models. We are just publishing on that, so that they take into account random effects, for example, right? Chromatography, resin lot, my blood cell attributes are different than yours, etc. So these kind of random effects can be taken into account here to set up these models. So I hope I could show you the bright side of this moon, what we can do with these kind of digital twins to get this going. Also, when we put it in real-time release, this kind of model, right, we can also run this in real time. So you see here, these 3 runs have been executed. The probability of these process parameters is now very narrow because we know exactly where we have run. And then we can, in real time, extrapolate from there how will be the quality if we would run the next 2 steps here, the missing 2 steps, with these kind of conditions. Yeah? And with this, we have a probability of failure which we can get in real time. Yeah? We have done that. It's not a mock-up. It's a software tool which we have developed, and it's available for use here. Yeah, so you see here finally how the product quality will probably fall into a certain probability spec at the end of unit operation 5. Okay. So we use different tools for real-time release here. Of course, we can use statistical process control on the right upper part here, right? Everyone is using statistical process control, but statistical process control is not really helping you. It's following a golden badge. But because if it goes out of a certain range, or this yellow range which you see there, what do? Okay? The expert meet and see what we can do. No, we have to have a direct, real-time, compensatory approach to get this right, okay? And only statistical process control doesn't tell you the root cause, what I have to change in order to get it back, okay? And our approaches, especially here with this integrated process model, helps you actually get the process back, okay? This finally goes into the point that we have to have adaptive process control strategies, and I show you probably a very complex plot, but I want to explain that, how we want to do that. You see on the left side, we see, of course, the life cycle here from the development to manufacturing. On the right-hand upper part, you see the manufacturing data. So you get the data from the manufacturing. All the data are probably, let's say, generated via the MES, EBR, etc., and so on. We get the data. We get the data together with the development data on the lower right corner. We have to link these things, manufacturing and development data. We assess with the data science approaches, which I have shown you, if, let's say, the control strategy is still okay or not, okay? If we probably run in the same, let's say, normal operating range, but just a set point a little bit left or right, it could be the one way, so we don't have to have any resubmission or anything like this. So it just recommends to run a little bit more on the left or the right side, okay? Or if, of course, it would be even better to redo the control strategy and change the normal operating ranges, okay? But this is an approach which we do very iteratively, okay? Checking out CPP, CQA relationships on that basis, linking manufacturing and development data together. That was the bright side of the moon. I just come to the part which we have discussed yesterday already. We need some data architectures, data management, some prerequisites on that, okay? One thing what we can do is analyzing MES data. We do that also, right? I come with a company, Kerber, which has, of course, the PassX tool here. And, of course, we analyze MES data alone. And you can plot them. And you can easily already look at that. You can probably have a look at yield optimization. But it doesn't really tell you why this is the case. It's mainly a dashboarding, right, here, this kind of thing. In order to get deeper into there, and really finding out why this is happening, you have to include more data, okay? Not only MES data, right? Because I also have the problem that some of the things are not hardly readable, but you see that. So the manufacturing part is on the top, okay? And then, of course, the PCS and the PD, the process development and process characterization parts, they have, of course, completely different data, okay? You, per definition, have, let's say, perturbed the system. If people ask me how many runs do I need to set up a digital twin, I say always it depends. 100 runs of a manufacturing run will not be sufficient because you have not perturbed intentionally all this kind of the process, right? You have probably variability which comes, like we have seen here, okay? But you don't know why, okay? So in order to really get to a control strategy, you have to link manufacturing data with development data. I think that's very clear. And this picture is probably more readable in this way. So the manufacturing is only the tip of the iceberg of the data. I can't really use them for a proper control strategy. Of course we use that, but mainly we have to link that to PCS and PD data, right? And we have to have means to get this done. Yeah? I think this is closer to what we have discussed yesterday. I show you a picture of how, I think I have to not to discuss that, right? This is a classical picture when we start doing our work. Lots of Excelings, lots of stuff, and of course this is not the way how we can work. Lots of manual interactions, lots of errors, also data streams which are not used at all for the analysis, etc. So I think you're all aware of this, okay? So we have to change This one, I think we have discussed it yesterday. But we have other difficulties, let's say, or challenges in order to solve that. And that's on this picture. We have to get data from across the complete unit operation, the complete process chain. We have to get the data across the complete life cycle, right? And we have to get the data from our partners, right? They all have to be together in order to do this holistic control strategy. There's no doubt on that, right? We are collecting all the data. I will not go too much into detail. We have REST APIs, data push tools, data crawlers, etc. in order to get that done. It's never an excuse. We always get the data imported, customized, configured, whatever. But the driving force needs to be the use case in order to get there, in order to do that, right? I think we have discussed it yesterday as well. So what we are trying to solve is getting all the data into one data matrix, okay? We have all the operations, we have all the life cycle approaches, and we get everything in one data matrix. But the data sources are completely different. We have time series, quality data, spectra, images, 2D data, 3D data, etc. If you would dump that all into if you give it to a statistician and he should find out CQA, CPP relationships just on these data, it would just be a mess, okay? You cannot dump a time series data like that, just like this, into data analysis, right? It needs context. We said this already. And there are multiple of tools which we have developed in the last 10 years on setting context. Automated phase setting, for example, of time series. Automated calculations of features from pictures. Extraction from pictures. Alignment to events. All these things can be done, okay? It's very important to have that automatic. In case you want to know more about it, we can talk about that. But data contextualization is not to be skipped, not at all, okay? And there are a couple of, let's say, manual tools, like I just discussed. But there are probably also other automated tools, which we assessed also recently here in these publications here, together with Anurag Rathore, probably you know him. And this is about knowledge management and finally getting to data contextualization. And here, this plot you see here on the y-axis, tools which are listed in literature, so the scientific view on this. And on the on the x-axis, you see the importance ranking by industry. Okay, and you see there are a couple of tools like T6, T7, T1, where you say, okay, we need capture tools, we need visualization. Yeah, we all visualize already in industry. I think we are fine there. I think that's a kind of knowledge management tool by visualization. That's fine. You see that some are centered. There's also the models in the simulation. T9, for example, this is modeled. But there are a couple of them which are very much in forefront in the publication space. This is T5 and T8, and these are taxonomies, ontologies, and intelligent agents. So let's put them all under the umbrella of ontologies here. In the moment we discuss taxonomies also. I believe that these tools are really a big enabler for automated data contextualization. Getting slowly to my conclusions here. This all binds into Pharma 4.0. You may know this slide here from ISPE, okay? And these are the ingredients, the 4 pillars. But we have data integrity by design and digital maturity as the enabler. And I would like, with the last slides, which I have, go a little bit on these 2 elements, data integrity and digital maturity. We need data integrity when we think about linking all this together, so the collection, the contextualization, and the visualization analysis here, you see on the right-hand side, we need to have that in one thing. I believe data management, collection, contextualization, and the analytics have to be in one tool. Because if you are creating an analytic plot, which is finally ending up in an IND, even in non-GMP, right? So we are in PD, PCS is still stage 1 validation, non-GMP. But we are creating plots which are finally ending up in an IND or BLA filing, something like this. This plot, we need to retrieve the root data source of this. And if you have a PCA plot or a multivariate data analysis plot, and you see, there's some outlier in there. If I take it out, it looks a bit different, and I take another out, it looks again, you know what I mean, right? These kind of things. You have to find out what was the real root data set in order to produce that plot. That's the reason why I believe this one really belongs together, very strictly. So that's about data integrity, in my opinion. Data integrity calls to combine data management and analytics. Conclusions. Give me 3 minutes for concluding on that. So we have to have a tool which links the pre-commercialization parts of the life cycle and the manufacturing together. I think I have shown you that a real control strategy can only be done by feeding these two data really together. We have identified a couple of use cases or business cases which we can approach. Here, especially with this end-to-end digital twin, just name some of them. We can set up the control strategy probably. We can also identify PPQ runs. We can set control limits. We can make real-time batch release, etc. We can do that with these kind of digital twins. Okay, these are real business cases which we are proceeding. Then I took some slides in from yesterday, our discussions, to see where are also the gaps here. We have two streams. We have the process life cycle, like I have just shown that, but we also have the clinical product life cycle, okay? And so these are the clinical phases. And I think, like I said yesterday, we have a data disrupt between these two streams, okay? Where are the clinical data result outcomes really are getting back to the control strategy? Okay, I think we have to have a meeting where we bring this together here, CMC plus clinical, okay, digital summit, where we put this together and see what kind of data do we need for the control strategy, right? And the hypothesis, on the other hand, is that I believe clinical studies are often with negative outcome because the process was not properly developed. Yeah, so we have a larger range of variability. You run quick and dirty to produce some clinical material and so on. So in this way, I believe if we would work together closer, I think clinical trial results would be more positive, right? We need a lot of tools for lifecycle management. It's not only about a PCA plot. There are lots of different tools which we need. We need data science. I will not go too much into detail in that. We finally, for Pharma 4.0, we have to link that to a data maturity model. I showed you the pyramid on the right side of the control strategy. And how does this map to the data maturity model? Here you see the different steps of the data maturity model. Step 1 and 2 are, of course, trivial. But then step 3 is what is happening. I think that's the status now. Yeah? Why is it happening? That's the control strategy, the process understanding, which we should directly have, right? And what I thought of bringing you over in this keynote are solutions for the other elements here in level 5 and 6. What will happen? Okay, so the predictive capability and also the adaptive capability. Okay, it's number 6. Okay, adaptive capability of the life cycle of the digital twin on the one hand, but also the adaptive capability of the control strategy. I hope I could show you that also here, what we need to do. Yeah, recommended workflow for robust control strategies along the life cycle. We need automated data management, ensuring data integrity. Generate process understanding using process characterization. Predictive power via digital twins. And then, of course, we need to link that into an MES, control the process understanding using MES and enabling CPV. I think these are the 4 steps which we see and which was aligned also with this good practice guide which we just published. With this, I thank you for your attention. Nice to be here. Thank you.